The Earth is our home. Our natural environment results from complex relations between the sun, the oceans, and the atmosphere. The polar ice and the tropical heat represent the extremes of our planet's climate. In reality, this is a very narrow temperature band, completely different from any other planet we've observed. The stability of the Earth's environment has allowed life to emerge, and life has changed the planet. As far as we know, the Earth is the only planet in the universe to have given rise to life. The Orion Nebula is a vast cloud of gas and dust in the Orion constellation. It's a place where new stars are being created. As part of the nebula condenses, it separates into clumps. As each clump contracts under its own gravitation, it begins to swirl, flattening into a disk. They're called protoplanetary disks, or proplyds. In the center of a proplyd, as the molecules are squeezed together, a fusion reaction begins and a star ignites. Some proplyds, occurring close to an established star, shine brightly under the influence of their neighbor. While this makes them easier to observe, the glowing gas and dust is being stripped away by the stellar winds from the adjacent star. Dark proplyds, only observable as silhouettes, maintain their surrounding ring of gas and dust. As the system matures, this stellar debris will form a planetary system. The Hubble Space Telescope has recorded numerous examples of this process, enough for astronomers to understand that the formation of planets is commonplace. This is how our own sun started its life 4.6 billion years ago. But the planets would take longer to emerge. Small grains within the disk began accreting, forming planetesimals. The larger a clump became, the stronger its gravitational attraction, in turn leading to more rapid growth. An early version of Jupiter would have been the first to coalesce, completely clearing its orbit. Around a core of heavy metal and rock, Jupiter's atmosphere, mainly of hydrogen, was compressed by its strong gravitation. Any solid surface lay beneath thousands of kilometers of liquid gas. Our observations of exoplanets have revealed Jupiter-sized gas giants orbiting close to their stars. Astronomers believe the young Jupiter would have begun a track toward the Sun, dragging asteroids and comets in with it. But Jupiter's inward path reversed as it was pushed into an orbital resonance with the emerging Saturn. Not all of the objects forming in the early solar system stayed orbiting the Sun. Smaller objects passing a planet would be deflected by the stronger gravitation, or even captured, becoming a moon. It is thought that there were up to 20 smaller planets orbiting in the inner solar system, from which the 4 remaining terrestrial planets were formed. At this time, collisions in the developing planetary system were common, and evidence from the Apollo moon rocks suggest an impact between the early Earth and an ancestor of our moon was important in our planet's evolution. The Earth has a larger than expected iron core, and gravitational analysis of the moon suggests its core is lighter than expected. A collision between the bodies would explain the moon's loss of much of its heavy material to the more massive Earth. The impact was a glancing blow that set the Earth rapidly spinning with a 5-hour day. The moon that we know coalesced from the molten debris. Although our moon is not the largest in the solar system, it is closer in mass to its parent planet than any other moon. The stabilizing effect that the moon has upon the Earth's rotation is significant. Over long periods, the Earth's axis will vary by as much as 1 degree. Without the moon's influence, this variation could be as much as 85 degrees, with drastic implications for the climate's stability. The debris in the early solar system was cleared by the planets in a period called the Heavy Bombardment. The emerging Earth was peppered with asteroids and comets, delivering water necessary for life. While tectonic forces erased the bombardment scars from Earth, the Moon, which endured the same travails, is still covered with craters. When chaos in the developing solar system settled down, the young Earth was in a unique position. The Earth's distance from the Sun was just right for the abundance of water on the planet to exist in liquid form. As the Moon had drifted away, the planet's rapid rotation had slowed, and the Sun's heat was evenly shared across the surface. The Earth's large metallic core, combined with the planet's rotation, meant that a magnetic field stretched out around the planet, deflecting the charged solar wind and protecting the surface from extremes of solar radiation. In a hostile universe, the Earth was a uniquely benign environment. The geological record shows that around 2.7 billion years ago, oxygen began occurring in the atmosphere. The vast iron ore regions of Western Australia were formed as iron in the oceans reacted with the new abundance of oxygen to form iron oxide. Simple plant life was using the sunlight and carbon dioxide to live, and it produced highly reactive oxygen as a waste product. This enabled more complex life to emerge, building an intricate web of interrelated plants and animals, completely transforming the planet. The change in the atmosphere had other dramatic consequences. Oxygen stripped much of the highly insulating gases from the air, drastically cooling the Earth. A sequence of ice ages began. Though there is an abundance of evidence showing planetary glaciation punctuated by warm periods, the factors triggering these cycles are complex. Fault lines are clues to the movement of continents, leading to diversions of ocean currents. The effect of volcanic activity on the atmosphere. And changes in the direction of the Earth's axis with regard to our planet's elliptical orbit around the Sun, all contributors to long-term fluctuations in the Earth's climate. Analysis of ice cores deposited in the Antarctic or Greenland is an accurate way to see how the composition of the atmosphere has changed over the previous 800,000 years. Bubbles of air caught between snowflakes before being rigidly trapped as the snow becomes ice can be accurately sampled. One thing is clear: carbon dioxide reaches a peak of around 270 parts per million during the warm periods and drops to approximately 170 parts per million when glaciation is at its greatest. But from this data, it's hard to know if extra CO2 causes the warming or the warming leads to extra CO2. In 1958, Dave Keeling, working for the Scripps Institute, began recording accurate levels of atmospheric CO2 at the Mauna Loa Observatory in Hawaii. It was the beginning of a unique record known as the Keeling curves. Keeling's graph revealed a seasonal variation corresponding to spring and summer in the Northern Hemisphere, where landmass and plant cover is greater. During the northern spring and into the summer, CO2 levels dropped because of the increase in photosynthesis. By the 1970s, a disturbing trend had emerged. CO2 levels were in a steady rise. At first, there was uncertainty about the implications. Extra CO2 could trap more heat, leading to a warming effect, known as the greenhouse effect. But some scientists were worried that aerosol pollution could attenuate levels of sunlight reaching the planet, resulting in a cooling environment. As the decades passed, different pieces of evidence were collected. Drill cores from the ocean floor revealed that ice ages had been triggered by Milankovitch cycles, the variations between Earth's tilt and its elliptical orbit. Though these effects were minor, the correlation was obvious. If such a small nudge could alter the climate, perhaps changes in CO2 could as well. Scientists were realizing just how poorly they understood planet Earth.
A Thor Delta rocket blasts aloft from Cape Canaveral, carrying a robot weatherman into orbit for America's...
At the beginning of the space age, scientists were keen to make weather observations from orbit. Launched in 1960, Tyros-1 was the first weather satellite. It was equipped with 2 TV cameras, regularly transmitting images of global cloud patterns. It provided meteorologists with a unique view, and it was followed by improved versions. Because these early satellites were in highly inclined low Earth orbits, the data gathered covered the whole planet, and it was shared across the world. Since 1873, nations had been cooperating on weather prediction via the International Meteorological Organization, which in 1951 became the World Meteorological Organization, an arm of the United Nations headquartered in Geneva. With a UN resolution calling for international cooperation in the peaceful uses of outer space, weather satellites of different nations were soon being coordinated for the benefit of all mankind. In 1964, the Nimbus program began. The series of 7 satellites included a more sophisticated set of sensors. Nimbus was a testbed for new technologies, and it gathered data about different areas. Along with cloud patterns was information about the atmosphere and sea ice. This was the pre-digital age, and all electronic image data was burnt to and stored on 70mm film. Little thought was given to establishing an archive for future reference. The Nimbus program was an early example of Earth observation rather than just a group of weather satellites. And meteorologists started seeing the planet as a complex and interconnected system. Today, a fleet of satellites is in operation, monitoring the atmosphere, the oceans, the ice, the land, and the biosphere. It is now understood that ice, particularly sea ice, plays an important role in the Earth's climate system. Polar ice slowly flows to the coasts where it melts, providing a source of cold water that drives the ocean currents responsible for the transfer of heat from the equatorial regions to the poles. These currents also move nutrition, which is important for the survival of life. Global winds also circulate water via clouds, keeping the land moist and able to support vegetation. Plant life in both the oceans and the atmosphere removes CO2 from the air and replenishes the atmospheric oxygen. Both the ice, known as the cryosphere, and the clouds reflect a proportion of the sun's energy back out into space. The extent of the ice and cloud cover are important factors in the Earth's energy budget. As ice melts, it exposes ocean or rock, which absorbs more solar energy. Similarly, cloud cover, or the absence of it, will have an effect upon the land or sea beneath. Vegetation is also an important climate factor, as land plants pump huge amounts of water vapor into the atmosphere. But things are changing. Humanity, simply through weight of numbers, is influencing key elements of the planet's climate system. In 50 years, the Earth's human population has risen from just over 3.5 billion to 7.7 billion today. More people need more resources. And while there have been revolutions in agriculture and in technology, the Earth's reserves are not limitless. In 1979, Europe began launching spacecraft. And while the new Earth observation satellites were revealing changes, scientists were reluctant to reach conclusions about long-term trends. They understood that there was a certain amount of variability in the planet's climate cycle. And though climate science knew about the steady rise in atmospheric CO2 revealed by the Keeling curve, researchers were looking for additional, solid evidence that change caused by human activity was happening. Since 1913, spectroscopy had revealed that a layer of ozone in the stratosphere blocked harmful UV sunlight from reaching the ground. In 1974, Mario Molina, a postdoctoral fellow working on hot atom chemistry, published a paper suggesting that the family of industrial chemicals known as chlorofluorocarbons, or CFCs, could damage the ozone layer. In the 1980s, meteorologists working in Antarctica found the evidence. The polar vortex above the southern continent concentrates the CFCs in the stratosphere. Mother-of-pearl clouds in the polar skies contain ice crystals which, in combination with ultraviolet, split chlorine from the CFC molecule. Each chlorine atom can break down over 100,000 ozone molecules. A large area centered over Antarctica showed almost no ozone. It became known as the hole in the ozone layer. The United Nations began talks aimed at limiting the production of CFCs, and in 1989, an international treaty, known as the Montreal Protocol, capped the production of CFCs and ultimately resulted in a 10-year phase-out of CFC production. All countries signed the agreement, and the Montreal Protocol is seen as a model of international cooperation. In the 1980s, an upward trend in global temperature averages was becoming clear, and a scientific consensus emerged that the burning of fossil fuels was altering the balance of gases in the atmosphere. Most of our planet's fresh water is locked in the polar ice caps. 61% of this ice covers the Antarctic continent. In the north, Greenland is also covered by an ice sheet. There is no landmass at the North Pole, but a large area of sea ice grows and shrinks with the seasons. Seasonal sea ice also fringes Greenland and Antarctica. Ice shelves are a third manifestation of polar ice. These are thick layers of ice that extend into the ocean from the mouths of glaciers. Periodically, icebergs will break away from these regions. These areas are important to the circulation of global winds and ocean currents. And since 2002, NASA has tracked the prevalence of water in general and ice in particular via the GRACE satellites, which were recently replaced by a similar pair of GRACE follow-on satellites. The two follow the same orbit, and minute changes in the Earth's gravitational field will cause them to change speed, with a variation in the distance between them. This data is accurately measured, allowing researchers to record changes due to variations in groundwater or in ice thickness. During the life of the first GRACE mission, Greenland lost 285 gigatons of ice per year. On average, Antarctica lost 137 gigatons per year. From 2005 to 2016, sea levels rose by 3.7 centimeters due to melting ice sheets and to expansion of seawater. Sea levels have been monitored from space since 1992, initially with the TOPEX Poseidon satellite, and more recently with the JASON series of satellites. JASON 3 uses a precision radar altimeter to measure regional and global variation in sea levels. In the 20 years to 2014, the average rise was 6 centimeters, but the increase is not uniform. The red areas show the greatest rise, with white representing no change and blue signifying a decrease. The unevenness of the sea surface is due to a complex interaction between ocean currents, the Earth's spin, and the topography of the ocean floor. All these factors must be accounted for to arrive at a baseline against which to measure changes. These blue areas in the Atlantic show a shift in the Gulf Stream. The Camargue region of southern France is a low-lying area at the delta of the Rhône River. In the 1980s, a seawall was built to prevent the encroaching Mediterranean. Over the last 30 years, the coastline here has been pushed back by several hundred meters. Scientists are convinced that a warming global climate is responsible, and that our reliance on the burning of fossil fuels has led to an excess of carbon dioxide in the atmosphere, which traps heat. 93% of this heat has been taken up by the oceans. Data from the Argo network of ocean buoys shows an average warming of 0.9 of a degree Celsius since the 1950s. While this may not sound like much, meteorologists understand how sea surface temperatures drive hurricanes and cyclones, and early predictions of storms of greater magnitude are being realized. Long-standing weather records are being broken and broken again. In 2017, NASA, NOAA and the UK Met Office all agreed that 2016 had been the hottest year on record. Globally, 16 of the 17 hottest years have all occurred since the year 2000. Both NASA and ESA have been monitoring the distribution and concentrations of CO2 in the atmosphere since 1992. This visualization from data collected in 2006 shows the yearly fluctuations of carbon dioxide and carbon monoxide. While most CO2 emanates from the populous northern hemisphere, seasonal fires in Africa, Australia, and South America generate much of the carbon monoxide. Prolonged droughts and more severe forest fires are another aspect accompanying increased levels of atmospheric CO2 that are currently unfolding. Such events inject a huge pulse of greenhouse gases into the atmosphere, magnifying the problem. The European Space Agency's Copernicus program, with its Sentinel Earth observation satellites, has committed to making information about the changing climate freely available to policymakers, businesses, and research institutions. Josef Aschbacher is ESA's Director of Earth Observation Programs.
What you see here on this graph is the CO2 concentrations of the atmosphere over the last 800,000 years. And you see that these values are going up and down in different phases. You see on the blue lines here are indicating ice ages, and the orange lines here are indicating periods between ice ages or periods where it's much warmer. But you also see that over the last 800,000 years, the value was always below 300 parts per million, and suddenly, since the last century, it goes up very steep towards 400 parts per million or even beyond.
Distinguished delegates,
The recent climate summit, COP25, held in Madrid, made little progress toward an international agreement to cut greenhouse gas emissions. While some businesses and economies will have to adjust, that task only gets more difficult as time passes, and far greater adjustments will be forced upon everyone. The Earth is the only place we know that harbors life, but the stability that has enabled this web of life is fragile. Plants and animals interact for mutual benefit. Our benign environment results from the complex and varied creatures with which we share the planet. It's important that we look after our home. The space industry is at a turning point. NASA's Space Launch System is about to fly. With it, the new Orion spacecraft, a collaboration between NASA and ESA, will target the Moon. A landing is scheduled for 2024. As far as the United States is concerned, low Earth orbit is now the province of corporations, with Boeing and SpaceX competing to break Russia's stranglehold on manned trips to the International Space Station. New technology is cutting costs and increasing launch frequency, with complex satellites being so small they can be deployed in new ways. Several companies are working towards space tourism. Virgin Galactic says its promised trips beyond the atmosphere should start happening soon. Since the retirement of the shuttle in 2011, space science has shifted focus to research carried out on the International Space Station and to robotic missions in deep space. During this period, all manned flights have been to and from the ISS, with the only viable spacecraft being the Russian Soyuz. This has cost both NASA and ESA billions in launch fees. Russia, Europe and Japan, major partners in the ISS, developed their own cargo craft to resupply the space station. But NASA tendered for private companies to take on these responsibilities. Rising star in the launch business, SpaceX, was contracted to develop a cargo craft that would launch on its Falcon 9 rocket.
3, 2, 1, 0. And launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
A second aerospace business, Orbital Sciences Corporation, now Orbital ATK, signed a contract for similar hardware and services. NASA is developing its own launch system and the Orion spacecraft, but it's designed for missions far more ambitious than resupplying the ISS. America's activity in low Earth orbit is being reallocated to the commercial sector, and NASA is helping with technology transfers. Agency administrators want two completely different systems, giving the space agency what they call dissimilar redundancy. When the space shuttle twice suffered catastrophic failures, NASA was stuck on the ground for years while exhaustive investigations were made. The redundancy approach will prevent this paralysis. In 2014, NASA signed contracts with Boeing and SpaceX to develop and test human-rated spacecraft to ferry astronauts to and from the International Space Station. It was a continuation of the dissimilar redundancy approach. The space agency has set performance criteria for the new craft and crew training, but is taking a hands-off approach regarding how the companies meet the requirements. Boeing's spacecraft is called the Starliner. It has space for 7 astronauts and will be capable of being used 10 times. NASA requires any human-rated spacecraft to meet higher standards of safety and reliability than a cargo craft, and new capsules must demonstrate, via a series of test flights, that they meet certification.
5, 4,
One crucial part of the new spacecraft is the launch escape system. It's the equivalent of a fighter pilot's ejector seat. Both Boeing and SpaceX have opted for a new method of capsule-mounted rockets to push the craft clear in an emergency, in contrast to the more traditional escape tower above the agency's new Orion spacecraft. The trial of Boeing's escape system worked well, with the exception that only 2 of the 3 parachutes deployed, but the problem is understood. The Starliner could continue to the next uncrewed launch to orbit. One of the novel features of Boeing's capsule is its ability to return to dry land, like Russia's Soyuz craft. Airbags, stowed behind the heat shield, inflate prior to landing. Without the need to deploy ships for an ocean recovery, there will be considerable savings. Though the capsule can fly on the Delta IV, the Falcon 9, and the yet-to-be-flown Vulcan, initial testing of the spacecraft has been with the Atlas V launcher. The Atlas ground support infrastructure has been modified to accommodate the Starliner with the addition of a crew access arm. The Starliner made its first unmanned test flight in December 2019. Its destination was the ISS. The launch was perfect, and 4.5 minutes after liftoff, the first stage separated. Next, the boost protect covers and the aeroskirt were jettisoned, and the Centaur upper stage burned for a further 7 minutes, following the course parameters perfectly. After separation, the capsule was in a suborbital trajectory, selected because it allowed a safe path back to the ground in case of a malfunction during the boost phase. To achieve the correct orbit, the craft was required to fire its 4 attitude and orbital maneuvering thrusters 31 minutes after liftoff. However, the Starliner's sequence clock was incorrect, and the orbit insertion burn did not happen. Ground control was able to salvage parts of the mission, but the craft was not able to reach the International Space Station. This setback will delay the Starliner's first mission carrying astronauts. SpaceX's Crew Dragon capsule is a refinement of the cargo craft that first flew in 2010. From the beginning, the Dragon capsule has had a heat shield, enabling it to return safely to the ground. No other ISS cargo craft has had this ability. In addition, the Dragon also has a window. This should have been a clue to SpaceX's long-term plans for the craft. In 2014, after the contract for a human-rated craft was signed, SpaceX began work on the Dragon 2. Like its Boeing equivalent, the Dragon 2 sits above a service module that can carry unpressurized cargo and includes a heat exchange unit and a coating of solar cells that does away with the moving parts involved in extendable solar wings. The Dragon 2 can accommodate 7 astronauts, though NASA has said it will generally only send 4 people at a time. Control interface is via a touchscreen. Cape Canaveral's Launch Complex 39A has been equipped with a crew access arm, and in March 2019, in a flight known as Demo 1, the unmanned craft made its first spaceflight. The Dragon carried a dummy astronaut, wired with sensors to monitor G-forces, and a small delivery of equipment for the ISS. The launch and the phasing maneuvers to align its orbit with the ISS were all correctly executed. The automated docking procedure went smoothly, and the Dragon stayed connected to the space station for 5 days. Decoupling from the ISS went as expected, and observers on the ground were delighted with the capsule's behavior. Throughout the mission, every aspect of the Dragon 2's performance was monitored. The craft's return to Earth was faultless, and the recovered capsule would be reused for the one remaining uncrewed flight test. SpaceX planned to use new capsules for manned flights and then recycle the craft for cargo use. Confident planners at SpaceX and NASA were looking toward the first crewed flight. The final certification test was an in-flight simulation of a booster failure that would monitor the Dragon's launch escape system. But before that, the craft's Super Draco engines, used in mission aborts, needed retesting. This was considered routine and had been carried out many times. A leaked video revealed an explosion that had destroyed the capsule. The problem was not engine failure, but a faulty valve. The flight test of the Dragon 2's escape system eventually happened early in 2020. But just as with the Boeing capsule, which was also well behind schedule, the explosion and the inquiry that followed were another unwelcome delay.
2, 1, 0. Ignition.
Around the point of maximum dynamic pressure, the core stage's engines were cut and the escape system triggered automatically. Shortly after, aerodynamic stresses on the tumbling booster caused it to explode.
Cheering in the room, bright flash there. It looks like that maybe Falcon 9 breaking up.
The certification test was a success, and the Dragon 2's next flight will carry astronauts. But there is another spacecraft in development that's worth mentioning. The Sierra Nevada Corporation's Dreamchaser. It's a lifting body craft designed to ride to orbit on an Atlas V, but return to the ground via a commercial landing strip. So far, the Dreamchaser's only flights have been glide tests. As a cargo ship, the Dreamchaser can return a 1,750 kilogram load to the surface. As a crewed vehicle, it is designed to take from 2 to 7 astronauts. The European Space Agency has shown interest in the craft, with the possibility of launching European astronauts atop of French Ariane. The craft will use the bipropellants methane and hydrogen tetroxide for on-orbit maneuvers, doing away with the highly toxic hydrazine. When the space shuttle landed, it had to be at a restricted runway where suited ground staff purged the craft of residual hydrazine. Originally in the running for a NASA contract for ferrying astronauts to the ISS, it missed out because Sierra Nevada could not comply with NASA's 2017 deadline for crewed missions. The favored contractors, Boeing and SpaceX, both failed to meet that same deadline. But the Dreamchaser has a contract for cargo missions to the ISS, and an expendable cargo module known as Shooting Star is being developed. The company still plans a human-rated version of the Dreamchaser, but it's unclear when the craft will fly.
Burn! 4, 3, 2, 1. Burn the hole! Burn the hole!
Cape Canaveral's Launch Complex 17 was the starting point for many historic Delta II missions. Since the demise of the Space Shuttle, NASA infrastructure from the earliest days of spaceflight has been eliminated. Since the heady days of the space race, NASA's budget has been steadily trending downward, and various launch sites have been given over to the private sector. While NASA has been overseeing the commercial craft that will continue to service the research work carried out on the ISS, its sharpest focus has been on the new Orion spacecraft and the giant space launch system that will boost it to orbit. After its establishment in 1958, the agency's challenge had been to master space technology and then to reach the moon. But since then, the exploration side of NASA's charter has been achieved by robotic missions. Now, a new plan called Artemis will return to the moon. It relies upon the Orion spacecraft and the SLS. The Space Launch System will be the most powerful rocket yet built. And although the design features the latest technologies, most of its components are derived from the Space Shuttle. The Block 1 version, which will send an unmanned Orion spacecraft to orbit the moon, features a central core that owes much to the shuttle's external tank. At the base of the central core are 4 RS-25 engines. The shuttle had 3 of these engines, and NASA still has 16 left over from the shuttle program. Although the engines remain the same, their control systems have been redesigned. Each one has been exhaustively tested, and when the original batch have been utilized, an upgraded version, the RS-25D, will be available. Flanking the central core of the Space Launch System are 2 solid fuel boosters. Again, a refinement of shuttle technology, but with each booster having 5 instead of 4 segments. The new design has been rigorously tested. The boosters will only burn for the first 2 minutes of flight, each consuming 6 tons of propellant every second and providing more than 75% of the rocket's thrust. Unlike the shuttle's boosters, these will not be reusable. The upper stage for the Block 1 configuration of the Space Launch System is called the Interim Cryogenic Propulsion Stage, the ICPS. It's a stopgap modification of the Delta Cryogenic Second Stage, used with the Delta 3 and 4 launchers. In 2014, a Delta 4 fitted with this upper stage lifted an Orion spacecraft to its first orbital test. The Orion, with a dummy service module, was boosted to a height approaching 5,800 kilometers, allowing it a high-speed return to Earth similar to a lunar mission. The much larger exploration upper stage was to replace the ICPS for the first crewed mission atop a Block 1B launcher, but design changes have led to delays, and the EUS now won't fly till the 4th Orion mission. The Orion spacecraft itself will comfortably accommodate 4 astronauts for 21 days, with the crew breathing air at atmospheric pressure. The craft is intended for missions beyond Earth orbit. It's designed to integrate with larger modular structures such as habitation modules, specialist landing craft, or the planned lunar gateway. Instrumentation and the control interface are primarily via a touchscreen. The digital control enables weight saving through the absence of wires and switches. The Orion Service Module is the European Space Agency's contribution to the craft. It's derived from the automated transfer vehicle which delivered cargo to the ISS. Oxygen and nitrogen cylinders in the service module supply air. There's a water storage tank, and wastewater is not dumped but recycled. A 4-wing solar array generates 11 kilowatts for battery charging and powering the electrical subsystems. For propulsion and maneuvering, the service module is equipped with a version of the same system used by the Space Shuttle. But like so many aspects of this spacecraft, the system can be easily replaced when alternate models under consideration become available. The third important piece of the Orion craft is the launch abort system, mounted above the capsule. 3 different types of solid fuel rocket are designed to fire at the first hint of a malfunction in the launcher.
1, ignition.
The system was tested in July 2019 above a Minotaur booster, a highly modified peacekeeper missile. Engineers were delighted with its performance. Launch infrastructure is being upgraded for the SLS, and there's increased activity in preparation for the first test of the big new rocket. There were celebrations as the core stage left the Michoud assembly facility. But it hasn't gone to Cape Canaveral, not yet. It was taken by barge to the Stennis test facility in Mississippi, where the stage will be powered up for a series of tests known as the Green Run test campaign. The date, or even the year, for the first launch has been put back a number of times, although it could be as early as 2020. NASA's Exploration Initiative received a jolt in 2019 when US Vice President Pence, the chairman of the National Space Council, called for NASA's Exploration Initiative to be accelerated.
It is the stated policy of this administration and the United States of America to return American astronauts to the moon within the next 5 years. But now's come the time for us to make the next giant leap and return American astronauts to the moon, establish a permanent base there, and develop the technologies to take American astronauts to Mars and beyond.
The existing plan had called for a moon landing no earlier than 2028. The month after the Vice President's speech, NASA announced the Artemis program, Artemis being the sister of Apollo. Late in 2019, companies were called to tender for a lunar lander and for a lunar space station known as the Lunar Gateway. The timeline calls for Artemis 1, an uncrewed Orion craft, to enter a series of looping orbits of the moon in 2020. Astronauts are in training for Artemis 2, due to launch in 2022. The current proposal will see a crew of 4 sent to a retrograde orbit of the moon in a flight that could last as long as 21 days. The powerful exploration upper stage will not be ready for this flight, and its proposed trajectory has been modified to accommodate the limited capacity of the interim cryogenic upper stage. During this time, the Artemis plan calls for commercial launch services to make a series of uncrewed flights to position elements of the Lunar Gateway and Lunar Lander in orbit around the moon. A contract has been signed with Maxar Technologies for a power and propulsion element. Some see this phase of the Artemis program as a weak link, because the US Congress has been reluctant to authorize additional funds. There are no concrete blueprints for a lunar lander yet, and some have suggested that the 2024 deadline is being pushed too enthusiastically. Artemis 3 will see a male and a female astronaut land near the lunar South Pole, where ice exists within permanently shaded craters. Long-term goals for NASA's Space Exploration Initiative include the development of technologies that will enable a landing on the surface of Mars. Finally, a different form of spacecraft will soon be taking passengers. Virgin Galactic will start taking paying customers to space in 2020. Everything about the company's spaceships, Enterprise and Unity, is reusable, and Virgin is building 2 additional spacecraft. Passengers will experience weightlessness for about 6 minutes. Virgin is also entering the satellite business with a launcher service using a 747 called Cosmic Girl, acting as an air launch mothership.